One of the most remarkable features of quantum mechanics, and there are many, is that sometimes things we think of as particles, like an electron, act like waves, and things we think of as inherently like waves, light waves for instance, can act like they're made out of particles. That duality between particle-like and the wave-like nature of things is really deep in nature, and it seems that depending on the kind of experiment we design, the kind of apparatus that we use, it'll actually pick out a wave-like or a particle-like behavior. That seems really strange, that our act of measurement would change the fundamental aspect of nature. Let's take an example. We know how waves behave. At the beach, you've probably seen plane waves coming in from a distance as they arrive at a beach. Just long waves along parallel to the beach arrival. We have a wave machine here, a tank of water that's got a little stick that's vibrating back and forth, generating waves. And these waves move across the screen from right to left. And what you're seeing, these bright lines, are the crests of the waves as they make that trip. Now, with the help of Wolfgang, who is going to insert a barrier here, something you might see, for instance, if there was a gap in a jetty going parallel to the beach, what you see is interesting. The plane wave arrives at the barrier, and where the waves are allowed to go through, they generate these wavelets, as if these circular waves are starting over here and moving out as they travel to the left. And if we have a second opening, as Wolfgang's about to install here, we see two wavelets, one of them generated over here and one of them generated over here. And here we see really the fundamental feature of wave dynamics that comes up over and over again anytime you study any kind of waves, whether they're sound waves or light waves, and that is that there's interference. And what you're seeing in this image is that along the center, you always have a crest meeting a crest or a trough meeting a trough, and so we see a wave coming along like this, straight down the center, symmetrically located like that. But if we go a little bit off that axis, we see a point where the crest from the upper hole is meeting trough from the lower hole, and similarly a trough from here meets a crest from here, and we see these bands that you can see like this or here, where crest is meeting trough and trough is meeting crest, and the two wavelets are annihilating each other. They're flattening themselves out. So if we were to have a seawall over here, we would see big splashes where crest was meeting crest and trough was meeting trough, and then there'd be parts of the seawall that correspond to these flat zones where there'd be practically no movement of water. This flattening of crest and trough and crest, is something you can see in your bathtub if you push your rubber duck up and down and the return wave crest hits an outgoing trough. Okay, what does this have to do with quantum mechanics? Well, if we imagine an electron to be like a little BB, we would expect that they would pile up at some line over here. So if we had a piece of photographic paper and an electron gun over here, like you have in an old-fashioned TV, and the electron would go out through this hole, you would think it would just make a little black spot in this photographic paper. Or it might make one over here. And we would expect to see a big bunch of black spots over here and black spots over here. Just the way if we shot BBs at this opening, we would expect them to make two piles, one over here and one over here. But interestingly enough, that's not what happens. What happens is that even if you let the electrons go one by one, so you're not letting two electrons go, only one by one, the electrons act like waves, and they seem to interfere with themselves. Each electron seems to be a kind of wave like this that goes out of the two holes. And so when they arrive at, say, a photographic plate over here, what we see is a dark zone where there are lots of electrons have hit the photographic paper, then a bright zone, then a dark zone, then a bright zone, then a dark zone, then a bright zone. It's as if electrons are like waves. But they're not just like waves. And if, for example, we were to measure whether it went through this hole or this hole, what we'd find is that it would either go through one or the other. If we attached a little coil linked up to a light bulb, for instance, we would either flash this one or this one. We'd never see them both flash, ever. So it seems that the act of measuring makes them behave like particles. And when they act like particles over here, they tend to pile up in a lot of black spots on our photographic paper over here or over here. In other words, they continue to act like BBs. So if we organize the experiment to test whether it went through one or the other, we ask a particle question, we get a particle answer, and they act like particles, and they arrive at the photographic paper like particles. If we don't ask the question which they went through, it's as if they go through both, acting like waves, they interfere with themselves, and what we get is alternating patterns of dark and light, as if they had, when they arrive here, or here, or here, or here, in one place only, but in aggregate, they make dark spots, light spots, dark spots, light spots, as if they had arrived as a wave interfering with itself. That's really strange. And the two aspects of that strangeness are, on the one hand, that particles like electrons can also behave like waves, but even more strange from a classical perspective is that the very act of measurement makes such a difference. So if you tried, for instance, to be really clever, if you said, I'm just going to put a coil over here, and if it goes through, it'll flash a light, but if it doesn't go through, if this light doesn't flash, then I know it didn't go through here, then it must have gone through there. Well, then what happens is it behaves the same way it did as if you had measured both of them. So just the act of measuring, of asking the question experimentally, did you go through hole on the upper side or did you go through the hole on the downside, is forcing nature into a new state. That's really remarkable. That's this very strange new world of quantum mechanics where we aren't separate from the nature we're observing. There are two take-home lessons from the two-slit experiment. The first is that particles and waves turn out, rather than being opposites or mutually exclusive, really are two different aspects of matter. The second lesson, related to the first, is that whether things behave like particles or waves depends on the experimental setup we construct, depends on the questions we're asking of nature. If we ask the question, did you go through this slit or did you go through that slit, we're asking a particle question and electrons will behave like particles. If we don't ask that, if we simply open two slits, creating an experiment that's open to the wave phenomena, then it looks like the electron goes through both of them as a wave, forming wavelets at the two openings. This is amazing. It really defies the expectations that we have from classical physics. That fundamental assumption that nature behaves as it does and that we, on the outside, can observe it to the extent that our skill and instruments permit. Quantum mechanics says otherwise. Quantum mechanics says we are implicated in the world. The order of nature and our order of measurement are fundamentally, inextricably intertwined.